The purpose of this video is to introduce you to new software that allows users to build interactive three-dimensional visual simulations. In order to demonstrate the software's features, an interactive simulation of the human cardiovascular system will be created. If you have any questions at all about the content of the video, please email Zach at zezzell@ufl.edu. Further instructions will be given at the end of this video. Now let's begin with the software demonstration. The software is called KOG. In order to create a dynamic simulation in KOG, we need to have a simulation model, or a mathematical definition of the simulation dynamics. For the human cardiovascular system, we can use the Benniken compartmental model for blood flow. Here is the model as published in Benniken's thesis. Here it is recreated in our design tool. Two fundamental components of KOG are the node and the relationship. You can see the nodes here represented by spheres and the relationships represented by edges between the nodes. Another important concept is the attribute, which can be assigned to nodes and relationships. We see here the attributes for the left ventricle. The KOG interface is connected to a compartmental model solver. So, because we've assigned the attributes volume, pressure, and flow to these nodes, and we've named all the relationships flows too, we can actually execute the simulation model. Here it is executing. Any numeric attribute, such as pressure, can be dragged into the scene for a more detailed view. We can also drag attributes onto pre-existing plots. For example, let's create a pressure volume loop for the left ventricle. Now that we have used KOG to encode the base executable simulation, we can build on this by making the scene more visual. For example, we can connect simulation dynamics to a 3D heart mesh in order to create an animation of a beating heart. To do this, you will need to obtain a heart model. You could purchase one online and import it into the scene by assigning it as an attribute to a node. Let's create a node for the heart. And assign it a mesh. We can also assign it a material. In order to animate the mesh, we'll need to link the simulation variable volume to the scale of a section of the heart mesh. We do this by adding a has-a relationship between the heart and its subcomponents, and then positioning the subcomponents in their corresponding locations of the heart mesh. Let's do this for the right atrium. Notice when we add the has-a relationship, the heart node becomes the graphical parent to the right atrium node. Next, we add a collection of influence attributes that determine the type of influence. First, let's add an attribute influence radius. We see the yellow sphere shows us which part of the heart will be influenced by the simulation dynamics of the right atrium. Other attributes we need to add include influence source, the variable that will drive the influence. For this, we want to use volume. Influence destination, the variable that will be affected by the influence. We are trying to create a beating effect, so let's set this to scale. Influence source min and max, and influence destination, min and max. These values denote the range of the influence source and destination values. Values outside this range will be mapped to either the min or max of the range. We see here that once the influence attributes are added, the vertices in the heart mesh are illuminated. This signifies that the influence is set up correctly. After the influence is set, we can tweak the values in real time to achieve the desired beating effect. After experimenting with different values while the simulation runs, we find what looks appropriate. We can do the same for the other 3 chambers of the heart. This is the result. Another feature of KOG is the ability to sculpt relationships into meaningful 3D paths. For example, let me sculpt the relationship between the right ventricle and the pulmonary arterial tree. Control points can be added to the relationships in order to interactively change the curvature of the edge. Here's the result after sculpting the entire simulation model. In KOG, particle systems can also be leveraged to visually relate simulation dynamics. To demonstrate particle systems, I will add blood particles that travel along the edges of the simulation model. The velocity of these particles will be linked to the simulation variable flow. Much like how we created an influence, we will need to assign a collection of particle attributes to the relationships. These attributes are particle emission, the variable that will influence the particle creation rate and particle speed. We'll assign it the value flow. Particle image, the image file that is used to render the particle. Here we will use cell.jpg. The particle color, the color that the particle image will be tinted. Particle emission factor, a scalar value to scale the amount of particles emitted. And there is also an optional attribute, particle random offset. This defines a distance which the particle is randomly offset from its path. Here I am just finishing up adding the particle emission factor attribute. Now we see particles start emitting from the source node and travel to the destination node. Let's decrease the particle emission factor a bit. The velocity of the particles are based on the simulation variable blood flow. Notice how the particles pulse near the extrathoracic arteries, but travel more smoothly near the veins. Now let's adjust particle color. This 3D vector represents the red, green, and blue values of the color. 000 is black and 111 is white. Here we see 010, which is green. We may also choose to link the color attribute to attributes in the source and destination nodes. Let's set particle color to presentation color. This is an attribute in the adjacent nodes. This way the particles will transition from red to blue as they travel along the relationship. Here is the result of adding particles to every relationship of the simulation model. At any point during the simulation, you can decrease the timescale for a closer inspection. Finally, I will explain attribute properties. You may have noticed I have been changing some properties of attributes as I have been constructing this visualization module. Consider the attribute resistance that is assigned to every flows to relationship. You can see the properties of resistance here. An attribute can be a variable, meaning it is numeric and potentially can be part of the simulation model. If it is a variable, then it can be a scalar or a 3D vector. 3D vectors are useful for graphical properties such as colors, positions, scales, and rotations. Any variable, scalar or vector, can be made adjustable. When a variable is adjustable, you can set the range of acceptable values. Sliders are provided for adjustable variables to enable interactive control. You can see here resistance is set to be adjustable between 0.001 and 1.0. Lastly, an attribute can be set to be visible in Viewer. If an attribute is visible in the viewer, then when your visualization is loaded in the KOG Viewer software, it can be viewed and potentially interacted with. Here's what our cardiovascular visualization looks like in the KOG Viewer. Notice only a subset of the attributes are visible, and that users are not permitted to add or remove attributes. Further, in the KOG Viewer, nodes and relationships are fixed in their position in space. The Viewer software allows users to interact with and view the dynamic visualization without it being obscured or cluttered by design features. This completes the presentation on KOG. If you would like, you may download the KOG Viewer and explore the cardiovascular visualization we created further. KOG Viewer requires Windows 7. The viewer comes with a brief tutorial and example lesson that leverages KOG and was created by a physiology professor. Regardless if you download KOG, please be sure to fill out the survey. You should have an email with links to the KOG software and online survey. Again, please email Zach at zezzell@ufl.edu with any questions. Thanks for your time.